Quantum numbers. We are all used to seeing various drawings and diagrams of atoms with the nucleus surrounded by electrons whose orbits take the shape of concentric circles. While a description is useful in some situations, it is not an accurate description of an atom. The most significant problem with this model is the visualization of the electron in a concrete location. In quantum mechanics, the location of the electron orbiting an atom is described by its wave function, which gives only a probability of where you might find it. This concept is called electron density. The square of the wave function reveals the distribution of electron density in a three-dimensional space around the nucleus, and is called an orbital. The distribution can be calculated via the Schrödinger equation, whose results form what is known as the quantum numbers. There are three different quantum numbers. The principal, or n, which tells the size of the orbital, angular momentum, or L, the shape of the orbital, and the magnetic, the m, the orientation of orbital in space and the number of orbitals. There's also a fourth quantum number that tells us spin. Now, according to our chart, there are four different values of L, or four different orbital shapes. The simplest is S, and is spherical in shape. In the n equals 2 shell, the p orbitals, and this is an S right here, and you can see the shape is a circle. The p orbital is available and looks something like a peanut. For this orbital, it can have three different values of m. Remember, the m number tells us the orientation in space, but more importantly, it tells us the number of orbitals that are available. In the case of p, the m value is -1, 0, and 1, so we can have up to 3 orbitals on the x, y, z axes of a Cartesian system. Moving on up to n equals 3 puts us at the d sublevel and gives us up to 5 orbitals. With n equal to 4, the f sublevel can hold up to 7 orbitals. Take a look at the images here to get a visual idea of what these orbitals look like in space. Note, the f orbital is not imaged, and it is difficult to visualize. Once you understand how the quantum numbers give rise to the orbitals, we can now move on to see what happens when we fill them up with electrons. We now have enough knowledge to begin solving the periodic puzzle, but first we must discuss the Pauli exclusion principle and what it tells us. That is, no two electrons can have the same quantum number. What does this even mean? Well, let's look at the simplest form, hydrogen. It has one proton and one electron. In its lowest energy or ground state, the electron will exist in the smallest orbital s in the n equals 1 shell. The next element in line is helium with 2 electrons. Mr. Pauli says no two electrons can share the same quantum numbers. Now let us remember the fourth, somewhat obscure quantum number of spin. This allows the 2 helium electrons to share the same s orbital in the n1 shell, so as long as their spins are opposing. When 2 electrons share the same orbital with opposite spin, they are said to be paired. We now have enough knowledge to build a periodic table from scratch. The electron configuration for hydrogen can be written as 1s1, where the first one is the principal quantum number, or n, the s is the angular momentum number, L, or subshell, and the last number is the number of electrons in the subshell. Here we have other ones for helium, boron, and neon, and you can see the same numbering system applies. Here we have the periodic table showing only the valence or outer electrons in each element. It is these outermost electrons that determine the electron's reactivity. Some patterns should stand out. Take a look at the noble gases to the right column. All, excluding helium, have a completely full p sublevel. This explains why they don't react with anything. The elements in the column to the left of it, in light green, are known as halogens. Halogen means salt producing, and because they only need a single electron to fill their p sublevel, they're highly reactive. Where can they get that single electron? How about an element with only one valence electron, such as the ones in the yellow leftmost column? Does NaCl ring a bell? As you see, one can take the entirety of the periodic table of the elements and begin to understand how elements relate to and react with each other via the configuration of the valence electrons. While many of the relations have been known for hundreds of years, it wasn't until the development of quantum mechanics that we understood precisely how the electrons were configured within each element. It is amazing to think how this level of understanding of what nature is made of can be traced back to a very simple question with a profound answer. Is it a particle or a wave?